This video is intended to supplement notes that you might have already gotten from a friend while you were absent, but really I just want to give you sort of the quick and dirty version of concavity and give you some helpful hints along the way. Now, depending on which class you're in, AB or BC, you might have a slightly different version of this notes packet. That's okay. All right, if at any point you need to pause and work something or go back, please do so. Or, feel free to just make entirely different notes if your notes packet is a little bit different than the one I have here. All right, so to start, we need to know what we mean by concave up and concave down, right? Because if you see in this video, both curves 1 and 2 are increasing. However, they are different. And the difference is what we call concavity. And the quickest way to determine if something is concave up or concave down is to determine whether the curve is part of a smile or part of a frown. And sometimes the easiest way to do this actually is to put eyes above the curve. Right? So curve 1 is smiling at us. Curve 2 is frowning at us. All right, same things for 3 and 4. If we put eyes above them, curve 3 smiles, and curve 4 frowns. So curve 3 is concave up, and curve 4 is concave down. And so now, on this first page, I had everybody select 3 distinct points on the curve and draw tangent lines at those points. And you'll notice that on those curves that are concave up, so in this case, that would be curves 1 and 3. The tangent lines on these curves lie below the curve. Then that's a nice surefire way to determine that these are, yes, in fact, concave up. In the case of curves 2 and 4, all of the tangent lines that we've constructed sit above the curve. So that's a surefire way to guarantee that these two curves are concave down. And that's what we sort of summarize in this little box right here, right? The curve is concave up. If its tangent lines lie below the curve, it is concave down if its tangent lines are above the curve. Moving on to the next page. On this page, our goal was to get comfortable identifying intervals of concavity. All right, so first we identified local extrema, meaning turning points, right? We classified the intervals over which the function was increasing and decreasing, right? Then we started looking for inflection points, and inflection points are simply points where the curve changes concavity, right? And they're a little bit tougher to pluck out than turning points, but you'll get an eye for it. And so if we look closely at x equal to -5, right, that's when the curve switches from being part of a smile to being part of a frown. And so then the curve continues to be concave down until it looks like x equals 3, this point right here, where the curve switches from being concave down to concave up, right? If we now sort of put some eyes over here, right? Now the curve's smiling again. And so just as how the easiest way to identify your intervals of increase and decrease is to first identify your extrema, the easiest way to identify intervals of concave up and concave down is to first find your inflection points. So take a look through this page and think about any questions you might have on that. Next page. All right, so what we had found before was a way to describe concavity graphically, right, in terms of where the tangent lines sit. All right, now we're going to find a definition for concavity that uses the first derivative. And so these are just the same 4 curves from before, all right, and I have done the same thing as before. I've labeled 3 distinct points on each curve and drawn a tangent line there. Now, curves 1 and 2 are both increasing. That is what makes the slopes of each tangent line positive, right? So because these curves are increasing, the slopes of their tangent lines are positive. However, if we assign some hypothetical numerical values to these slopes, for example, on curve 1, 1/2, then 1, then 2, we recognize that the slopes on curve 1 are positive and increasing. If we assign hypothetical values to the slopes on curve 2, these slopes are positive but decreasing. So if we go back to curve 1, the fact that the slopes are positive tells us the curve is increasing. The fact that the slopes are increasing tell us that the curve is concave up. And so that's what we put down in this little box here, right? If a function is concave up on an interval, then f prime, the slopes of the tangent lines, are increasing on that interval. And similarly, we could conclude that if a function is concave down, then f prime, the slopes of the tangent lines, are decreasing. And this holds true for curves 3 and 4 as well. Both curves 3 and 4 are decreasing. That's what makes all of their slopes negative. However, if we look at curve 3 and assign some hypothetical slopes here, right, -2, -1, -1/2, at first it looks like the slopes are decreasing because they're getting less steep. But if we read the numbers in the correct sequence, -2, -1, -1/2, those numbers are increasing because they're getting less negative. Okay, so that's what makes this curve concave up, right? The slopes are still increasing. Similar for curve number 4, right? The slopes -1/2, -1, -2. Initially, you might be tempted to say that these slopes are increasing. However, they are getting more negative, which is technically decreasing. So again, because the slopes are decreasing, curve 4 is concave down. And so that's a nice way to define concavity in terms of the first derivative. Next page. Okay, and so on this page, all we did was we looked at the table. It's going to be important to note that this table displays values for f prime, not for f. Okay, so when asked over what intervals does f appear to be increasing, we would say -4 to 1, because on the interval -4 to 1, the slopes are positive, right? F prime of x is greater than 0. And so then on 1, 4, we could conclude reasonably that function f is decreasing because the slopes are negative. And now, when asked about whether function f appears concave up or concave down, we would not look at the sign of the slopes, we would look at the trend in the slopes. And we would see that as we read our slopes from left to right, our slopes are decreasing. So that would tell us that this curve is probably concave down. And example number 8 is very similar. All right, in this case, I would say that function g appears to be increasing on the interval 1, 4, because that is the interval over which the slopes are positive. And I would say that function g appears to be decreasing from -4 to 0, because that's the interval over which the slopes are negative. And now in this case, as we read the slopes from left to right, this sequence of numbers increases, always. So because f prime is increasing, this curve must be concave up. Next page. All right, so now we're going to figure out what concavity means for the second derivative. Okay, and that's because we already know the first part of this first bullet. If a function f is concave up, f prime is increasing. However, if a function is increasing, we know something about its derivative. If a function is increasing, its derivative is positive. So if f prime is increasing, then f double prime must be positive. Similarly, all right, second bullet point, if a function is concave down on an interval, then f prime is decreasing. And we know that if a function is decreasing, its derivative is negative. So everywhere where function f is concave down, f double prime will be negative. Okay? And so now, if a function has an inflection point, right, it's changing from concave up to concave down, or vice versa, all right, that means that f prime is either switching from increasing to decreasing, or switching from decreasing to increasing. And so that must mean that that f prime has a turning point if we're changing concavity. And so at a turning point on f prime, its derivative must be 0, or it could be undefined, right? We could have undefined slopes at turning points if they're sharp. So just as first derivatives inform us about a curve's intervals of increase and decrease, a function's second derivative can inform us about concavity. All right, so we just took a look at some examples about how we can use the second derivative. All right, so for number 9, all right, we were given a function, and it said determine whether f is increasing or decreasing. And so increasing or decreasing tells me to look to the sign of f prime. So we found f prime, and we checked its sign at 1, right? We got that that was -8, and so because we had a negative slope at 1, we must be decreasing at 1. Now, in part B, when we were asked to determine whether f was concave up or concave down at 1, the fact that I'm being asked about concavity tells me I'm going to be interested in the sign of f double prime. So we found f double prime, and then we checked the second derivative at 1. We found that the second derivative at 1 was negative, so we concluded that f was concave down at x equal to 1. And so now, in part C, if we're asked to find the inflection points of f, we know that we are looking for places where the curve is changing concavity. In other words, where f double prime will be switching from positive to negative or negative to positive. And that could happen where f double prime is 0 or where f double prime is undefined. And so in this case, right, we're only going to have to worry about f double prime being 0 because it's a polynomial, so it will not be undefined anywhere. And so in this particular case, f double prime is 0 at x equal to 0 and x equal to 2. So those are potential inflection points. Before we can be sure that they're inflection points, we'll want to make sure that the curve actually changes concavity, right? That the second derivative actually switches sign. And so that's exactly what we do in part D, right? We provide our potential inflection points, right, on our little number line here, and then we tested f double prime at values in between our potential inflection points. And we found that we do indeed change sign at each of these zeros of f double prime, so therefore we are concave up everywhere where f double prime is positive, and concave down everywhere f double prime is negative. Next page. So the great part about the second derivative is that it gives us information about what is going on. And so actually what I had people do first is this part right here. All right, I said sketch for me a local maximum and sketch for me a local minimum. And we determined that if we are at any local maximum, right, as long as the curve is smooth, the graph is always concave down. And if we are at a local minimum and the curve is smooth, we are always concave up. So this tells us something, right? And that brought us up here to the second derivative test, right? So the second derivative test does the same exact thing as the first derivative test, it just does it differently, right? It's used to classify extrema as a max or a min. So this first part is very important, right? So if f prime of c is 0, all right, so if your first derivative is 0, right, so you have a potential turning point. All right, so if your first derivative is 0 and your second derivative is positive, oh, well, if the second derivative is positive, that means my graph is concave up, so c must be a local minimum, right? If I'm at a potential turning point and my second derivative is negative, well, then I must be concave down, so c must be a local maximum. And unfortunately, if it turns out that the first derivative is 0 and the second derivative is 0 or undefined, then the second derivative test fails and we can't really conclude anything, but that's the way it goes. So in example 10, all right, we used the second derivative test to classify extrema, okay? So first we found the extrema, all right, and because I was looking for extrema, that told me that I was looking at f prime. And so when I set the first derivative equal to 0, I got two critical numbers here, and my first derivative will never be undefined, so I didn't have to worry about that. And so now I've got my two critical numbers, right? I know that the first derivative is 0 there, so let me just check the concavity at each of those critical numbers. And it turns out that at x equal to 0, the second derivative is positive, so my graph must be concave up, so 0 must be a local min. And then at x equal to 2, my second derivative was negative, right? So at my turning point, I am concave down. Therefore, x equal to 2 must be a local max. So when you're working with polynomials, the second derivative test can be a lot quicker than the first derivative test for classifying your extrema. It's basically just finding our critical numbers and saying, hey, am I concave up or concave down? Because that tells me if I'm at a max or a min. That's it. Next page. And so now in number 11, I gave you a function, and we said classify the extrema using the first derivative test. So this isn't really new, right? But just to review, right? So first we found critical numbers, right? And then we did this, in the calculator. We let the calculator handle this mess, and we got 3 critical numbers, right? And so we set up a number line, and we tested f prime at select values in between our potential turning points, right? And then filled out the sign chart accordingly. And so now we applied the first derivative test, right? We were able to say that x equal to 0 must be a local max because f prime switches from positive to negative, and that x equal to 0.8 is a local min because f prime switches from negative to positive, and x equal to 2 is nothing because f prime doesn't change sign, so it's probably just a saddle point. And so now we'll do the same thing, just using the second derivative test. So of course, right, if we're looking to classify extrema, right, we want to get our extrema first. Fortunately, we already did this in part A, so it's the same 3 numbers. All right, except now we just test each critical number in the second derivative, right? So these were our 3 critical numbers, and we said, okay, the second derivative at 0 is negative, right? Therefore, at 0 I'm concave down, so 0 must be a local max. At x equal to 0.8, the second derivative is positive, so my graph must be concave up, so 0.8 must be a local min. And then we get to y double prime of 2, and we see that the second derivative is 0 as well, and so that's when the test fails. I know, we don't like it, but that's the way it is. And so here you would have to use the first derivative test to be really, really sure about what is going on. And we know from our previous work exactly what it is, right? It's just a saddle point. All right. Concavity and turning points and inflection points. All right. In general, right, if your curve is smooth, you will never change concavity at a max. You will never change concavity at a min. All right. However, all right, if we start letting our curve be not smooth, we can have a different story here. All right. So in order for a turning point to also be an inflection point, I have to go, right, I have to change my increasing, decreasing behavior, and I have to change my concavity. So for example, all right, I could start out increasing concave up and then switch to decreasing concave down. That would make this point right here both a turning point and an inflection point. Or I could start, I don't know, how about decreasing concave down and switch to increasing concave up. Right? So it's possible to have a single point be both a turning point and an inflection point. It just makes your curve not smooth. That's all. All right, so I hope this video was helpful to you. Feel free to email me with any questions you have. Good luck.